A very small amateur rocket is at rest on a launch pad. The mass of the rocket is 100 kg, 90% is fuel, so 90 kg of it is fuel, 10 kg of it is metal, I suppose, and the fuel is ejected at 9 kilograms per second at 100 meters per second. This begins and the engine is fired up at t equals 0. What is the rate of the rocket? What is the weight of the rocket before takeoff? So before takeoff, the rocket is sitting here on the launch pad, and it has a mass of 100 kg, and so the weight will be 100 times 9.81, which is 981 newtons. So that is the weight of the rocket. What is the reaction force of the rocket before takeoff? Well, reaction and weight must be equal because it hasn't moved, it's not moving. So that was also 981 newtons as well. What is the thrust at the moment of takeoff? So when the rocket is fired up, it will have an extra thrust force, and the thrust is the mass times the mass per second, the mass ejected per second times the velocity at which it's ejected at. So that will be, let me see, you're told it's 9 kilograms a second ejected at 100 meters per second, so that is 900 newtons of thrust. Okay, next, what is the reaction force at the moment of takeoff? So at the moment of takeoff, these two must be greater than or equal to this. So right at the very beginning, we have T plus 4 equals W. So that is 900 plus or must equal 981. So or must equal 81 newtons. Okay, why doesn't the rocket take off? Well, interestingly, it doesn't take off because the thrust is 900 newtons, but the weight is 981 newtons, so there's not enough thrust force from the rocket to lift it. It's 81 newtons short. When will it take off? Well, the good news is the rocket is always burning fuel, which means its mass is reducing. So it will take off the moment that the thrust can be greater than or equal to the weight. The thrust is providing a constant upward force of 900 newtons, so we need the weight to equal 900. So that will be when the mass of the rocket is 900 divided by 9.81. So when the mass of the rocket is 91.74, it's losing 9 kilograms a second. So basically after 1 second, roughly 91.7 kg. So basically after 1 second, it's light enough to take off. How long will the fuel last for? Well, there's 90 kilograms of fuel, and it's burning at 9 kilograms a second, so obviously that's 10 seconds. Finally, what is the maximum height of the rocket? Okay, so after all this now we can get something interesting calculated. How high up will the rocket go? So, the rocket's burning its fuel, it's heading, has an up force of 900 newtons, it has a weight. And just like in the previous problem, the problem here with the weight is that the mass is changing, so we have to approximate the mass. So in this story, the rocket starts off at 100 kilograms, but at the end, when it burns off all the fuel, it's only left to be 10 kilograms. So it's on average 55 kilograms. So on average, its weight is, for the flight, 539.55 newtons. So the total net force up is 900 minus 539.55, and Newton said that should equal MA. So 900 minus the previous answer divided by 55, so that's an upward acceleration of 6.554. meters per second squared. Let's see now. U, V, A, T, S. How high does it go? If it is burning the fuel for 10 seconds, so the T is 10, the S is what we want, the A is 6.554, and the U is 0, and we're looking for the S, so we'll go with S equals UT plus a half A T squared. Okay, so just multiply out here, and the S is 327.68. Now, it'd be good to work out the V as well. So V is U plus AT, so the V would be 65.54 meters per second. Now that's not actually the end of the story, because after the fuel runs out and the rocket is now only 10 kilograms in mass and there's no more fuel, it still has an upwards velocity of 65 meters per second, so it will continue up in the air and stop and fall back down. So now we have another UVATS problem. UVATS. This time the U is 65.54 and the V is 0. The A is minus 9.81 and the S is what we want. So we'll go with V squared equals U squared plus 2A S. Let me just box that off. So for the second situation, the S will be 65.54 squared over 2 times 9.81. So that is 65.54 squared divided by that. So that's 218.9 meters. So that's nearly, well, not nearly, but it's a significant amount of the journey that it still has to go. Adding this to the previous answer, and we get 546.6, the total height, 546.6 meters then. Okay, we have to make some approximations in this question, like ignoring air friction, taking the mass to be an average value of 55 and so on, but believe it or not, even if we were to be more accurate and consider friction and the fact that the mass is changing every second, the answer is actually not too far away from this, so it is a pretty good approximation, definitely worth doing because it makes everything a lot simpler to calculate.